We live in difficult times, and I thought I would begin by expressing my thoughts to the millions of people who are suffering from economic difficulties, serious illness, and death due to COVID-19. All these people have our sympathy and thoughts. Well, here are the main topics of my talk: the Gauss circle problem, the Dirichlet divisor problem, two related identities from the lost notebook of Ramanujan, which have occupied my thoughts for many years. And then I have a number of things have arisen from these two identities in Ramanujan's lost notebook. And I'll tell you about some of these consequences and ongoing research. I like to begin always with my favorite photograph of Ramanujan, the most famous photograph of him. This was his passport photo taken in England before he returned to India. The unfortunate thing about this photo is that he had lost considerable weight before the photograph was taken. And so normally he had a much fuller complexion. The photograph was taken in his room at a nursing home because he was unable to attend or go to a photographer to have his picture taken. So he's actually in pajamas and bathrobe in this photograph and not in a suit as you might expect. So there are four photographs of Ramanujan. Oh, here is a picture of Ramanujan. I've had to leave my office after retiring at the University of Illinois, and my 9-year-old granddaughter Elise wrote on the board for the next people who will occupy my office. So she drew a picture of Ramanujan. Well, I've been invited to talk at a conference on special functions in discrete mathematics. So let me justify the invitation. So Bessel functions appear in these two remarkable identities and will occur at various times in my talk. Well, the two topics that I would like to talk about, as I indicated, are the circle problem of Gauss and the divisor problem of Dirichlet. So Ramanujan had an interest in these problems arising in India before he went to England. So let me quote from Ramanujan's first letter to Hardy. So on page 3, item 4 in this letter, he says that 1, 2, 4, 5, etc. are numbers which are either themselves squares or can be expressed as a sum of two squares. So from elementary number theory, we know that such numbers are a power of 2 and the product of primes congruent to 1 modulo 4. Then he said that the number of such numbers greater than a and less than b is a constant times this integral, which you see, plus an error term, theta of x. And he says that k is 0.764. Theta of x is very small compared with the integral. He says that they have been exactly found, though complicated, but he actually doesn't give them in his letter to Hardy. There's a slight misprint. Theta of x should be replaced by theta of b in the letter. So I copied the letter exactly, or the passage in the letter exactly the way Ramanujan had it. Although he doesn't give the value of k, actually he gives it later in his notebooks. And here is actually the value of k. R runs through the primes of the form 4m plus 3 in this infinite product. Well, this is really an amazing result. So let me quote Hardy: the dominant term, kb log b to the minus a half, in Ramanujan's notation, was first obtained by Landau in 1908. So Ramanujan had none of Landau's weapons at his command. It is sufficiently marvelous that he should have even dreamt of problems such as these problems which it has taken the finest mathematicians in Europe 100 years to solve. And then G.N. Watson said the most amazing thing about this formula is that it was discovered apparently independently by Ramanujan in his early days in India, and it appears in its appropriate place in his manuscript notebooks. Indeed, it really is remarkable that he could arrive at this estimate for the number of integers that could be represented as a sum of two squares without any background or familiarity with what was really going on in number theory at that day. It's absolutely remarkable achievement. So this result is actually on page 307 in Ramanujan's second notebook. So let me remind you that the second notebook is the main notebook. It has 255 pages of organized material, and this is followed by about 100 pages of unorganized material. So this result is in the unorganized material of the second notebook. Now, surprisingly, Ramanujan sketches a proof of this claim in the third notebook. This is really a surprise because there are virtually no proofs in the notebooks, and only very occasionally does Ramanujan give any kind of indication that of his proof. So more space, the entire page is actually devoted to his heuristic argument, and there are no other proofs or arguments in the notebooks as detailed as this one. Now, Watson said that the result was in his notebooks. He evidently was not familiar with the entire page devoted to this formula in his notebooks. So the copy of the notebooks that Watson was working with was a copy of the notebooks that was made at the University of Madras and sent to Hardy in 1923. So we don't know for sure if this third notebook was actually included in this shipment to Hardy, which again was copied by Watson. So evidently he did not have a copy of the third notebook. Well, that's not exactly the problem I want to talk with you about. I just wanted to indicate Ramanujan's initial interest in sums of squares as we know about it. So here we're looking at the number of different representations of a positive integer n as a sum of two squares. So we denote this by R2 of n, and we count different signs in different orders as distinct. So for example, 5 is plus or minus 2 squared plus or minus 1 squared. So we get 4 representations there, and then you could reverse the order of the summands. So altogether then, R2 of 5 is equal to 8. So each representation of n as a sum of two squares can be associated with a lattice point in the plane. For example, if you take the representation 5 equals minus 2 squared plus 1 squared, you can associate that with the lattice point minus 2, 1. And then each lattice point can be associated with a unit squared. Of course, there are 4 possibilities. We just should be consistent. So we'll be consistent by taking the unit square for which the lattice point is in the southwest corner. Okay, so in other words, if I want the number of representations of an integer for n less than or equal to x, numerically, that's exactly the same as the number of lattice points in a circle of radius square root x. And that number then is exactly equal to the sum of the areas of these squares, which you see in my picture, where each square is such that the lattice point is inside the circle radius square root x. So an approximation for the number of lattice points in this circle radius square root x, or the number of representations R2 of n less than or equal to x, is approximately the area of the circle. Okay, and that area of the circle is pi times the radius squared, pi x. But there'll be, of course, an error term. Some of those areas of those squares is not exactly equal to the area of the circle. Yeah. So I have a prime on this sum to indicate that it is such that if x is an integer, we only count a half R2 of x. The reason for this is that in analytic discussions of this summatory function, the natural sum that appears is this one with the prime on it. Then. Okay, so the question is, what is the order of magnitude of the error term of P of x? And Gauss was the first person to examine this. So R of x, the summatory function, well, certainly all those areas of squares, all those squares lie in a circle of radius square root x plus square root 2. And then if you take the circle of radius square root x minus square root 2, that's entirely red. No. Okay, so this is then a lower bound. So if you combine these two estimates together, the upper and lower bound, you get that R of x is pi x. And the error term is then big O of square root of x. Okay, let me explain the big O notation for those of you who might be unfamiliar with it. We say that f of x is big O of g of x as x tends to infinity. If there are constants c and x0 such that for x greater than or equal to x0, f of x in absolute value is less than a constant c times g of x in absolute value. Well, as many of you know, Ramanujan came to England at the invitation of G.H. Hardy. And very shortly after Ramanujan arrived, Hardy wrote a paper, an epic paper on sums of squares. And at the beginning of the paper, Hardy states this formula for R of x, or the sum of R2 of n. So the error term is then represented as a series of Bessel functions. So here is the definition of the ordinary Bessel function, J nu of z, which I'm sure almost all of you are familiar with. Yeah. Now, in the paper, Hardy says, the form of this equation, that is this identity, was suggested to me by Mr. S. Ramanujan, to whom I had communicated the analogous formula for d of 1 plus d of 2 through d of n, where d of n is the number of divisors of n. I find this expression rather strange because he said the form of this equation was suggested to me. Well, if you have the form, you really have the equation itself. So I'm not sure why Hardy expressed this in this way. So this is a result that Ramanujan must have had. Maybe he derived it in 1914 after he arrived in England. My guess is that he had derived this formula before coming to England. So it's now known as the Hardy-Ramanujan formula. Well, this is the asymptotic formula for the Bessel functions as mod z tends to infinity. So this is normally what's used to study upper bounds for the sum of R2 of n and less than or equal to x. That is upper bounds for the error term. So if you put in this term, you get an absolutely convergent series, and of course that's trivially bounded. But with this term, you do not get an absolutely convergent series, only a conditionally convergent series. So upper bounds then are obtained by a careful examination of this trigonometric series. And it's because we cannot accurately or estimate the series like we would this is the reason why we do not have today the exact upper bound. Well, Sierpinski showed that the error term is big O of x to the 1/3, improving on Gauss's result. So this result is in 1906, prior to the paper of Hardy. So what Sierpinski did was to actually use a weighted form of the identity. The R2 of n was multiplied by x minus n. This sum can also be represented as an infinite series of Bessel functions. The advantage is that the series converges absolutely. But the problem is, and this caused the difficulty, is that you have to work from this weighted sum back down to R of x, the unweighted sum. So that proof is much longer, so to speak, than the proof that we have today. So currently the best result in this direction, so again, this comes from estimating the trigonometric series that we get from the asymptotic formula for the Bessel function. This is due to Huxley in 2003, and this is his estimate for the error term. So note the exponent 131 over 416 is 0.3149. So in 114 years, mathematicians have been able to improve the error term by a little less than 0.02. Yeah. So, and to get from Sierpinski's result to Huxley's result, there were about 15 intermediate results. The best result is actually slightly better in this, in that the x to the epsilon is replaced by a multiple logarithmic term. Well, in this paper of Hardy, he gives this beautiful formula of Ramanujan. It's not given anywhere in Ramanujan's work. So it really is a beautiful formula. So note you get from the left side to the right side by just replacing or interchanging the A and the B. Really a very beautiful formula. So here we have two results in Hardy's paper. So we might ask, well, how many formulas of Ramanujan have been lost? These two formulas do not appear in Ramanujan's notebooks, nor do they appear in any of his published papers. Now, if we differentiate this formula with respect to B, let A tend to 0, replace B, 2 pi square root B by S, use analytic continuation, then we get this identity. And in fact, it's actually this identity that Hardy used in his study of the error term P of x. Now, to be fair to Hardy, he actually had another proof of this identity. So this is the key identity in Hardy's proof that the error term is omega plus or minus x to the 1/4 as x tends to infinity. So for those of you not familiar with this notation, let me explain it. So on the plus side, Hardy is indicating that there's a positive constant C1 in some sequence xn tending to infinity, such that the error term is bigger than a constant times x1, xn to the 1/4. And then on the minus side, Hardy's result says that there's a positive constant C2 and another sequence xn prime tending to infinity, such that the error term is less than minus C2 x prime to the 1/4. So in other words, the error term can get very large in the positive direction and very small in the negative direction. So most mathematicians feel that Hardy's result is close to the final result. In other words, for every epsilon greater than 0, the error term is big O of x to the 1/4 plus epsilon as x tends to infinity. So we have a huge gap between the conjecture that most number theorists feel is true and our best upper bound for P of X by Huxley. Well, let me just briefly discuss an identity of Jacobi, which is often proved in the first course in elementary number theory. R2 of n is the sum 4 times -1 to the d minus 1, where d runs through all positive odd integers. So if I take the sum of this, of R2 of n, so I just plug in what R2 of n is, but I write it in terms of the trigonometric function sine. So this is exactly the same as this, as you can easily check. Okay, then this sum over all divisors of n and n less than or equal to x, you can think of this as a sum over all pairs dj less than or equal to x. Okay, and then if you take the sum on j first, the sum on j first, square brackets of x over d, where square brackets of x is the greatest integer less than or equal to x. So we have this elementary formula then for the summatory function R2 of n, n less than or equal to x. Well, I might mention that in the original formulation I gave, n is greater than or equal to 0. So here, R2 of 0 is equal to 1. So 0 is represented by 0 squared plus 0 squared. Well, there's a remarkable identity for involving R2 of n, which is found in a one-page manuscript published with Ramanujan's Lost Notebook. So let me remind you that in the Narosa publication of the Lost Notebook, we not only have the Lost Notebook, which George Andrews found at Trinity College, Cambridge in the spring of 1976, but many other partial manuscripts and of Ramanujan that evidently were sent to Hardy from the University of Madras in 1923. So let me state Ramanujan's claim, the first claim. So he defines f of x to be the greatest integer function if x is not an integer, and x minus a half if x is an integer. So this really is the same as putting a prime on the sum. So here is Ramanujan's first identity. So J1 of x again denotes the ordinary Bessel function of order 1. So for theta between 0, 1 and x greater than 0, Ramanujan has the sum of f of x over n sine of 2 pi n theta. Here are the main terms, and then we have a double series of Bessel functions. So this was first proved with my co-authors, Sun Kim and Alexander Zaharescu, in 2013. And here is a picture of Sun Kim and myself taken at her getting her PhD. So she's my former PhD student. Well, here's a theorem of myself and Zaharescu. And this results from 2006. So you might ask, well, why did I say that Ramanujan's result was first proved in 2013, when here I have a proof by myself and Zaharescu in 2006? So why do I state this theorem or state these two different references? Well, if you're pondering there and trying to think why I did this, note that I've inverted the order of summation from what Ramanujan stated. Here I'm summing on n first and then on m. And here I'm summing on m first and then n. So it turns out that if we reverse the order of summation, it's somewhat easier to prove the identity. And the two proofs are completely different. There's nothing that we could use in our first proof of the inverted sum in our second proof. They're entirely different proofs, and we couldn't use anything for our first proof. So let me make a few remarks on this. So note that sum on the left-hand side is just a finite sum because it has a square brackets of x over n in it. So once n is bigger than x, we get 0. So note the case when theta is a quarter. Now remember this sum that we just gave you, the elementary sum. So on the left-hand side, if theta is equal to quarter, we get exactly the sine of pi d over 2. So the identity is sort of a mixture of, on the left-hand side, of just an elementary identity. So there's a third version. We can interpret the double sum as the product of mn tending to infinity. So Sun Kim's our rescue and I also proved the identity in this formulation. And it's possible that Ramanujan actually used this formulation, but we really don't know. The proof is much different, entirely different from the other two proofs. So in summary, we have three different theorems, three different ways of looking at Ramanujan's formula. And any one proof is completely different than the other two proofs. So the big question is, can we use this extra parameter theta to attack the circle problem? So often in analytic number theory, if we can introduce another parameter to work with, then by specializing that parameter, we might be able to get a new theorem or improved result. Unfortunately, no one has been ever able to use this parameter to attack the circle problem. So we would love to know what Ramanujan was thinking when he derived this formula. And then lastly, remember that the sum of R2 of n less than or equal to x had this formula, the Hardy-Ramanujan formula. So with the introduction of another parameter, essentially we're replacing then the single sum by a double sum in Ramanujan's formula. So if you take Ramanujan's formula and then actually plug in theta equals a quarter, this is actually the double series that you get when you specialize theta. Okay, so now let me go to the Dirichlet divisor problem. And again, in Ramanujan's first letter to Hardy, he indicates an interest in the Dirichlet divisor problem. But probably he never knew about Dirichlet and his interest in any of the interests of other mathematicians before him. So he says, let's take the number of divisors of n. So he indicates the first 10 values of n and the number of divisors. And then he says the sum of such numbers to n terms is n times 2 gamma, this is Euler's constant, minus 1 plus log n, plus 1/2 the number of divisors of n. So this is not quite correct because of the error term. These terms indeed are the main terms in the sum of the divisor. So this was a bit optimistic. This is not quite correct. Okay, so let me just discuss the sum of the divisors function d of n in an elementary way first. So I'm just separating these two by, okay, I have a misprint here. This is d star of x with no prime. This should be d of x with a prime on the sum, where the prime is the same as before in the summatory function for R2 of n. Again, it indicates that if x is an integer, then we count only a half d of x. Okay, so without the prime, let's just look at d star of x. So here is really the definition. So just as before, we can think of this as a sum over all pairs, dj less than or equal to x. So again, we sum on j first and get square brackets of x over d. Now, okay, so we have this very elementary formula for the sum of the divisors function. So again, as I've indicated, if d is a divisor of n, we look at n as the product of j, d, and observe that this divisor is uniquely associated with the lattice point dj. It'll be in the first quadrant, because d and j are positive, and it'll be under the hyperbola ab is equal to x, because the product dj is less than or equal to x. So d of x is equal to the number of lattice points in the first quadrant under or on the hyperbola ab equals x. So really, I guess I should have d star of x here, or it's d of x if I count those actually on the hyperbola with weight a half. So Dirichley's divisor problem is equivalent to the problem of finding the number of lattice points under or on a certain hyperbola, as I've given here. Okay, so here is hyperbola AB equals x. So the sum of d of n, n less than or equal to x, is the sum of the is the number of lattice points under this hyperbola. So the way one can get an estimate for the number of lattice points under the hyperbola, and I'm sure that Ramanujan proceeded in a similar way, is to do the following. You pull out a square of radius square root x. Then you estimate the number of lattice points in this region and the number of lattice points in this region, which of course are the same. But then we've counted the region here in the square twice, so we have to subtract that off. Okay, so here we have d star of x, d less than or equal to x of x over d. This is the number of lattice points in the first region. My divisors are all less than or equal to square root x on the left side of the square. And then here we have those, so to speak, the horizontal part, exactly the same, but we have to subtract off those in the square. So that's just square brackets of x squared. Now we replace square brackets of x over d by x over d plus an error term, 0 big O of 1. Of course, we can describe that error term more precisely. So we have two of them. And then I write square brackets of square root of x as square root of x minus the fractional part of square root of x. Okay, and this is just a simplification here. And the sum of big O of 1 is big O of square root of x, of course. And then here I get minus x, and then the rest of the other two terms are big O of square root of x. Okay, this is a partial sum of the harmonic series, and here I've indicated a familiar result. So I use this familiar result here, and then I just simplify what I have. And so this is what Ramanujan actually gave in his first letter to Hardy, except that he was optimistic about the error term, and this argument only produces an error term of big O of square root of x. So this is the argument that Dirichley used, I think, in 1854, 1856, something like that. Okay, so again, remember that these two are essentially the same, except for we're counting the lattice points on the hyperbola itself in this sum with weight 1/2. Okay, so here we have a summary of what we've just shown. So the sum of d of x this is the main term. And you might say, well, what's this 1/4 doing here? We can stick that in the error term. Well, the reason the 1/4 is here is that in analytic investigations of this sum, there's just naturally a 1/4 appears in our analytic investigations. So the error term is really, of course, the sum of these, but equivalently, we will study delta of x. So this is the error term, and Dirichlet showed it's big O square root of x. So the Dirichlet divisor problem asks for the correct order of this error term as x tends to infinity. Well, the first person to work on this, as far as we know, is Voronoi in 1904. He showed that the error term is big O of x to the 1/3 log x. So this is an analog then of Sierpinski's result in 1906, that for p of x, the error term in the sums of square problem is big O of x to the 1/3. Well, there's an identity for the sum of d of n less than or equal to x in terms of Bessel functions. So I'll define y nu of z in this way. And the Bessel function k nu of z is defined in this way. So these are familiar Bessel functions in the theory of Bessel functions. And if nu is an integer here, then we take the limit as nu tends to n, the integer n. Okay, so here we have a formula for the error term in terms of Bessel functions. So I1 is this linear combination of y1 and k1. So again, in the analytic investigation of the sum, this is the sum of Bessel functions that naturally arises. And there are well-known asymptotic formulas for these two Bessel functions. So this part is very similar to what we have for J nu. And this is similar as well. Here we have exponentially decreasing terms. So in our examination of the error term here, this is really important part because the other expressions here in these asymptotic formulas are give a series which is bounded, converges absolutely. Okay, so this is just sort of what I said. Examining these asymptotic formulas, we conclude as before that the series on the right-hand side of our formula converges conditionally, but not absolutely. And the conditional part comes from the sign. And this was the starting point for Voronoj's formula. So again, the other terms then can be bounded very easily by the power of x much smaller than what we have for delta of x. So the estimates for delta of x mirror those for p of x. So because the trigonometric series are very similar, if you have a result for one of the error terms, the same kind of argument works for the other error term. So the second identity on page 335 in the publication of the Lost Notebook is very similar to what we had before, but instead of the sign, we have a cosine here. And instead of the Bessel functions J1, we have the I1 Bessel function. Okay, so note what happens on the left side when theta is equal to 0. When theta is equal to 0, we just get this elementary sum representation for d star of x that we derived just a few minutes ago. Now, if we invert the order of summation and assume that we have convergence for one value of theta, then we can prove the identity for all values of theta. So I emphasize that we're inverting the order of summation here. And we can also prove the identity when the product mn tends to infinity. And again, Sun Kim's rescue and I proved these results in our paper in Advances in Mathematics. But I emphasize that these two methods of proof, or these two formulations, are not what Ramanujan had stated. We first thought, actually, that Ramanujan's formulation was incorrect. we did some numerical work and found that the series converges much more slowly for the the I1 Bessel function series than for the J1 Bessel function series. In the first case, there's a minus sign separating the Bessel functions, and the second a plus sign. We don't know if that's really important or not, but there seems to be less cancellation. So this was actually the last problem that Andrews and I faced in our editing of the lost notebook. So let me go back to Watson and what he called the final problem, an account of the Mach theta functions. So in this paper in the Journal of the London Math Society in 1936, he gives a detailed account of Ramanujan's last letter to Hardy, in which he introduced to Hardy and the world Mach theta functions. So Watson called this the final problem because the Mach theta functions were the last creative ideas, as far as we know, of Ramanujan. So he took this title for his paper from a well-known story, The Adventure of the Final Problem. This is a famous Sherlock Holmes story. It's actually the last story that was written by Sir Arthur Conan Doyle. And in these Sherlock Holmes stories, Sherlock Holmes' famous sidekick was Dr. Watson. So there are two reasons, I guess, that Watson chose this title for his paper. Namely, it was indicated the final reasoning or final topic that Ramanujan studied, possibly the final topic. And then Watson was a famous sidekick of Sherlock Holmes. But for us, as I indicated, the final problem is this identity involving the divisor function d of n found in this one-page manuscript in Ramanujan's lost notebook. And fortunately, I can tell you that actually the final problem has been solved. So it was solved by Zarescu, his PhD student, Junshin Lee, and myself. And we published it again in the, I shouldn't say again, but in the Journal of the London Math Society as Watson published his paper. And we have a more general account of that problem that is for a broader audience. This will appear in a book dedicated to George Andrews. So George Andrews, 80 Years of Combinatory Analysis. So these are the editors. I hope I didn't forget anyone. So this will be published on the last day of this year. So if you want an account of this final problem, which is not technical, then I recommend our paper here. And here is a picture of Junshin Lee and Alexander Zarescu. Junshin Lee is now a postdoc in Germany. So let me say a few words about this proof. We actually use some of the ideas that Sun Kim, Zarescu, and I used in the paper that I previously gave you. We also use some ideas in a paper that Zarescu and I wrote with Atul Dixit and Narendra Roy. So let me make a few comments on the series identity. Again, the series on the right-hand side does not converge absolutely. And so what we did in our proof is to take these terms which appear in the denominators of the series. Maybe I'll go back quickly to that series. Sorry, a long ways back. Okay, so these are the kinds of denominators that we have. So sorry, let me go quickly to the okay, so what we did is to replace the square roots by general complex variables. And then we're going to use analytic continuation. So a careful study of the series involving these complex variables shows that we can get uniform convergence with respect to theta in any compact subinterval 0, 1, provided we have these conditions on the real part of S and W. So they're different if X is an integer from those when X is not an integer. So as you might guess, if X is not an integer, we can do better than if X is an integer. We use the asymptotic formulas, as you might guess, for these Bessel functions. And to get these estimates that we need, we had to divide the interval into values of m and n that are either small or large, and we had to then estimate the sums separately. And we also had to separate the cases when x is an integer from that when x is not an integer. Okay, and so the bulk of the proof arises from estimating these trigonometric sums. But then after that, we have to show the equality on both sides. So we note there are discontinuities on both sides because of the at all of the integers. So on the left-hand side, it's because of the square bracket function. And if you remember on the right-hand side, you have this logarithmic term involving sine squared of pi theta. So then what we did is to isolate the Bessel functions on the right-hand side after multiplying both sides by sine squared of pi theta to get rid of the discontinuities. And then we just calculated the Fourier series of both sides and showed that the Fourier series are identical. And because both sides are now continuous, after we multiply both sides by sine squared of pi theta, we can appeal to the uniqueness theorem for Fourier series to conclude that the functions are identical. But to get to this place where we could apply the theory of Fourier series, we had to show that we could apply theory of Fourier series, and we had to estimate these trigonometric sums to get uniform convergence in order to make our applications. So you can think of a number of representations of an integer n as a sum of two squares as representations by a positive definite quadratic form. So you might ask, are there similar formulas for other positive definite quadratic forms? Yeah. Okay, so maybe I'll go through this a bit hurriedly. So here we have a Kronecker symbol, generalization of the Legendre symbol. M is a positive integer, n is a positive integer, coprime to the discriminant of a positive definite primitive integral quadratic binary quadratic form. And then we say R of n is the number of representations of n by a representative set of positive definite primitive integral binary quadratic forms of discriminant D. And then there's a formula of Dirichlet which gives you the number of representations provided you have all of these conditions satisfied. And this W here has three different values. These are, so to speak, unique, and then for all the rest of the values, we get two. Yeah. So, and this is again the Kronecker symbol. So if D is -4, that's the form we were dealing with in the first part of our talk. So let's look at when D is -3. There's only one quadratic form in this case. It's x squared plus xy plus y squared. So we can get a formula for R3 of n, and then also in other cases when you just have one of these quadratic forms, representations satisfying those conditions that I just mentioned. So one can derive then a formula for R3 of n, the number of representations of n by this quadratic form. We have the condition, though, that 3 does not divide n. And so we have this then series, double series of Bessel functions in this representation for R3 of n. So we can get similar formulas, which admittedly we haven't done, but the same methods will work in the cases when there is just one form in this class of forms. So we found out, that is Zawarescu, Sun Kim, and I, that we could also derive representations for other kinds of sums, besides the one I just gave you, in terms of, that is, representations in terms of double series of Bessel functions. So in a paper that we wrote in Krella, we examined 3 trigonometric sums. So here we have a product of 2 sines in our sum, and then we looked at sums involving a sine and a cosine, and then a cosine and a cosine. But in those 2 sums, we did not have the weight mn here. I won't give you the representations for these sums in terms of Bessel functions, but just tell you a couple things about what one can deduce then. So involved in work with these sums, we have characters. So chi1 and chi2 are not primitive odd characters modulo p and q then. And then we define this sum here. So d of chi1, chi2 is this sum. So this is sort of analogous to the sum of d of n when we're summing over all divisors d of n. And this one is j, or n over j equals n over d in our previous notation. So instead of having then dj, we have characters at d and at j. And then we put that in not just d of n, we have this weight of n now. Okay, so I hope you can see that this is somewhat of a weighted analog of what we were discussing earlier. We now have characters instead of just one appearing here, and we stuck in a weight. Okay, and it turns out that we can represent the sum in terms of this complicated looking sum of over all characters, chi1 mod p, chi2 mod q. These again are odd. These are Gauss sums, and again, d star of x is this analog of d of n. So remember that Hardy discovered or proved an omega theorem for p of x. And we're going to conjecture that, although I've put this in a different form, a different kind of or same kind of result. So analogous to Hardy, we're able to show, or able to conjecture, this is our conjecture, but we can't prove, in contrast to Hardy, that this sum of sines divided by x to the 5/4 is the lim sup is infinity. In other words, we can find a sequence of xn tending to infinity and a constant c such that the error term is bigger than a constant times x to the 5/4. And similarly, we can examine, get a big O result. And this is our big O result, or excuse me, this is our conjecture. So in other words, we could, this is also conjecture, and this is another conjecture. where the power x to the 5/4, analogous to what Hardy did, we think that this is the actual order of the error term. We can prove this, that the order of the error term is big O of x to the 17/12 plus epsilon. Okay, so note the difference. 5/4 is 1.25, and this is 17/12 then. Okay, so again, there's a discrepancy from what we conjecture and what we can prove. So let's look at that. In the special case when theta and sigma are equal to 1/4. So this is again what we have in our sine sum. We get 2 of these. Okay, so here our double sine sum becomes this when we substitute in 1/4. Okay, so you can then rewrite that in this way because m and n are odd. Yeah. So again, remember, we get 0 if n is even. Yeah. Okay, so this is somewhat of an interesting lattice point problem. What we are doing is counting lattice points under or on the hyperbola AB less than or equal to x. But what we require both coordinates to be odd, and we're putting a weight on the sum. Namely, we have the lattice points themselves, so to speak, on the sum. Okay, so this is analogous to the divisor problem of Dirichlet, except that it's weighted and by a power of -1 and the lattice point coordinates themselves. So we studied this initially in this paper, but the results which I recently told you are part of current research that is just beginning with Martino Fasina, Sun Kim, and Alexandru Sarescu. So it'll be quite a while yet before we can publish anything. So let me just put these results of Hardy and others in a more general setting. So this is a setting of Chandrasekhar and Narasimhan. So we have an infinite sequence lambda n tending to infinity, another one mu n tending to infinity. These are sets of coefficients, and they form 2 general Dirichlet series. And usually in these series, the lambdas and mu's are constant coefficients times n. So 2 pi n, for example. We assume the Dirichlet series satisfy a functional equation like this. So analogous to what we have for the Riemann zeta function and for the generating function for sums of squares. Okay, so this is a sort of a complicated theorem, but let me just intuitively give you what this is saying. So this P of x arises from the singularities of our left-hand side of the functional equation. Okay, and so these singularities are enclosed in some curve in the complex plane. So we assume that this is the situation, just a finite number of these, and can be contained in some compact set. Okay, and then Chandrasekhar and Narasimhan show that you can get this theta or modular relation. Yeah. So for the Riemann zeta function, it's the familiar transformation formula for theta functions. Okay, and then we have another theorem. So again, this arises from the singularities of chi of s. And now we have an exponent rho greater than this. So r is the number appearing in the functional equation. This is the abscisive absolute convergence of psi. So we get what is called a resum identity. So what we've been looking at in this lecture is the case when rho is equal to 0. So for this resum identity, we can get then an identity in terms of Bessel functions again. So again, we had only looked at the case when rho is 0. Okay, and the great theorem of Chandrasekhar and Narasimhan is that any one of these two identities implies the other. So as I said here, let me go back again. So here is the resum identity. And the theorem says that the resum identity implies the functional equation, and the functional equation implies the resum identity. And each of these, again, of these three identities, they imply the other two. So we have three equivalent identities. So let me give you an example. So let's consider the Ramanujan tau function. So this is its Dirichlet series. This Dirichlet series satisfies this functional equation. The chi of s is an entire function. So in other words, the p of x term is 0, and the q of x are 0. So here is the modular relation for the tau function. Here is the resum equation involving the tau function. Okay, so here are three main objects: the functional equation, the modular relation, and the resum. And any one of these identities implies the other. So in particular, for this example, if rho is greater than 0, we have uniform convergence in any interval. If rho is equal to 0, we don't have uniform convergence, but we have bounded convergence, provided that we have no integral values. And if rho is less than 0, but bigger than -1/2, we have uniform convergence if we don't have any integral values of x here. So this, all this material is from this famous paper of Chandrasekhar and Narasimhan. So here's briefly one other example. If you look at Rk of n, where k is greater than 2, then the Dirichlet series satisfies this functional equation. Here we have the theta relation involving the sums of square function. Again, Rk of n is the sum of the number of ways of writing n is the sum of k squares. And here is the resum identity involving Rk of n. However, note here that k is greater than 2, so the power here is positive in this representation. In other words, we don't get a formula for the sum of Rk of n by itself in less than or equal to x. Okay, so question I've asked for several years is the following: do there exist analogs of Ramanujan's two series identities for other arithmetical functions, for example, tau of n, that are generated by Dirichlet series satisfying a functional equation? So in other words, in the general setting of Chandrasekhar and Narasimhan, can we find other arithmetic functions where we get then these double series representations of functions for the summatory function, or maybe for the resum generalization? So that's the one of the two major questions that I have. The other is, as I mentioned earlier, how can we use Ramanujan's identities with this extra parameter to attack the famous circle and divisor problems? So these, for me, are the two major questions that one can ask about Ramanujan's two formulas. So thank you very much for your invitation to speak with you in this meeting.